A context-free grammar, abbreviated CFG, is a set of rules that tells how strings can be built, like a cookbook for making sentences. A grammar is called ambiguous if there is at least one sentence, or string, that can be cooked in two or more completely different ways. Formally, let G be a CFG and W a string in the language L of G. G is ambiguous if and only if there exists a W in L of G such that there are two distinct parse trees, or two distinct leftmost derivations, for W. In other words, the same W can be derived by following different sequences of rules, giving two different tree shapes. This is the exact test we use to call a grammar ambiguous. Think of a simple math expression like 1 minus 2 minus 3. You can read it as 1 minus 2 then minus 3, which is first subtract 2 from 1, then subtract 3, or as 1 minus the result of 2 minus 3, which is keep 1, subtract the result of 2 minus 3. Both ways give a correct reading, so the grammar that allows any sequence of minus without saying which one binds tighter is ambiguous. The classic programming language example is the if-else statement. If B1, if B2, statement 1, else statement 2. The else could belong to the inner if B2 or to the outer if B1. Because the grammar does not decide, the sentence is ambiguous. These everyday puzzles illustrate why ambiguity matters. Explanation. To see ambiguity mathematically, write a tiny grammar for the expression example. E turns into E minus E or num. Derivation 1, leftmost. E implies E minus E implies E minus E minus E implies num minus E minus E implies num minus num minus E implies num minus num minus num. Derivation 2, rightmost. E implies E minus E implies num minus E implies num minus E minus E implies num minus num minus E implies num minus num minus num. Both derivations produce the same string num minus num, but the parse trees are different. Tree A, an E node with two E children. Tree B, an E node with left child num and right child E, which itself has two E children. The two trees correspond to the two groupings open parenthesis 1 minus 2 close parenthesis minus 3, and 1 minus open parenthesis 2 minus 3 close parenthesis. Because we can draw two distinct trees for the same string, the grammar is ambiguous. The question, is this grammar ambiguous, cannot be answered by a single computer program for all possible grammars. It is undecidable. This is similar to trying to write a universal recipe checker that can tell for every possible recipe whether it can be cooked in two totally different ways. Mathematically, such a checker does not exist. In practice, language designers use heuristics. Look for productions that can generate the same prefix in more than one way. For example, two rules that start with the same non-terminal. Generate a lot of sample strings up to a certain length and try to build two parse trees. If a clash is found, the grammar is ambiguous. Use parser generator warnings, yak bison report shift/reduce, or reduce/reduce conflicts as clues that ambiguity may be present. These tricks do not guarantee detection for every grammar, but they catch most real-world problems. A common way to remove ambiguity is to embed operator precedence directly into the grammar. Instead of one rule E goes to E minus E, we split the expression into layers. Expr goes to expr plus term or term, term goes to term times factor or factor, factor goes to expr or num. Here star binds tighter than plus because term is used inside expr. For the minus example, we could write expr goes to expr minus term or term, term goes to num. Now the only possible tree for num minus num is left associative, so the grammar becomes unambiguous. The same idea works for if-else. Force the else to match the nearest if by introducing separate non-terminals for matched and unmatched statements. These constructions keep the language the same, they generate exactly the same strings, but give a single clear parse tree for each string. Deterministic parsers such as LL1, LR0, SLR1, and LALR1 rely on a single choice at each step. If a grammar is ambiguous, the parser faces a conflict. Two possible rules compete for the same look-ahead symbol. In an LL1 table, you would see the same entry filled twice. In an LR table, you would see a shift-reduce or reduce-reduce conflict. The parser cannot decide which way to go, so it either aborts or guesses, which defeats the deterministic guarantee. Therefore, an ambiguous grammar cannot be used directly with these parsers. It must be rewritten into an equivalent unambiguous form, as in the previous point before building the parsing tables. Some languages are inherently ambiguous. No matter how cleverly you rewrite the grammar, you will always end up with at least one string that has two different parse trees. A classic example is L equals the set of a to the IB to the JC to the K such that I equals J or J equals K. Any context-free grammar that generates L must be ambiguous because the string A to the NB to the NC to the N can satisfy both conditions I equals J and J equals K, and will have two distinct derivations. Ambiguity is also preserved under many closure operations. If L sub 1 is ambiguous and R is a regular language, then the intersection of L sub 1 and R is still ambiguous. Similarly, the union, concatenation, and clean star of ambiguous languages are ambiguous. This means that once you have an inherently ambiguous language, you cannot hide the ambiguity by combining it with nicer languages. The problem sticks around. Compilers deal with ambiguity in several practical ways. Design an unambiguous grammar from the start, using precedence levels and separate matched or unmatched constructs for if-else. Declare precedence and associativity to parser generators, for example %left- in Yak, so the tool resolves conflicts automatically. Use context after parsing. Many languages let the parser build a partial tree and then a later pass decides which else belongs to which if based on the nearest uncle rule. Employ disambiguation rules such as the else matches the closest preceding, if that does not already have an else. Test with sample programs and look for shift-reduce conflicts. Fix the grammar iteratively. By following these strategies, real-world compilers avoid the chaos that ambiguity would otherwise cause, ensuring that every source program is translated in exactly one predictable way.